The last section of this chapter focuses on what are called Lewis acids and bases. And this will be the same scientist who gave us the Lewis structures. We'll see, while this type of definition of acids and bases is not as useful for Gen Chem, we will see it being very much useful in organic chemistry. So we will learn the foundation now. We'll see that Lewis acids are going to be lone pair acceptors. And Lewis bases are lone pair donors. And I'm saying lone pair, but really electron pair would also suffice in this definition. So we're looking at things that may not be explicitly acidic or basic. For example, what my OChem students are learning last week, or 2 weeks ago maybe, concerns the following. We notice that the aluminum here, although we may not be familiar with drawing Lewis structures for ionic compounds, the aluminum chloride, we have an empty p orbital here on the aluminum. It only has 6 electrons. So we have an empty p orbital. So we're going to see that what can actually happen is one of these chlorine lone pairs can go and attack the aluminum. We say attack, that's just the way we describe it, but it's going to donate its electrons to the aluminum. The chlorine has a lot of electrons, a lot of lone pairs. The aluminum is missing an octet, so the chlorine can go ahead and bond with it. And this is an acid-base reaction in which our Lewis base is our Cl2, and our Lewis acid is our aluminum chloride. So when this reaction actually happens, we end up with the following. All these lone pairs. Okay, here we go. We formed a new compound. And with this, we'll see that this will be a product of an acid-base reaction that involves no hydrogen whatsoever. Another common one is using NH3, which we'll draw out. Notice how nitrogen has this lovely lone pair here, and something like boron trifluoride, again, missing that extra pair of electrons of the boron, the nitrogen can go ahead and attack it, forming a product in which our boron and nitrogen are now bound together. And we're going to have some charges here, some formal charges. But we see that the ammonia has donated its lone pair to the boron. The ammonia, therefore, is a Lewis base. The boron trifluoride is a Lewis acid. Because these definitions are more useful in organic chemistry, we explicitly say Lewis acid and Lewis base when we're talking about this definition. When we just say acid and base, we typically mean in chemistry Bronsted-Lowry acids or bases. So that's one where we have proton donors, proton acceptors. That said, we could expand this definition to what are called the Lewis acids and bases. And again, we kind of see this with complex ion chemistry, where metals are binding with anions, forming complexes, which is something we'll study at the very end of the semester. But suffice it to say, this is just an example, a glimpse into the future of what you might see in organic chemistry, because you'll have a lot of Lewis acid catalysts there in OChem. And so that concludes our section here. And just for our notes, I'm going to go ahead and note here, this is our Lewis base, and this here is our Lewis acid. So Lewis acids have that empty p orbital, and the Lewis base has the extra lone pair.